back for another chapter. With the time frame for the field appraisal and field development completed, we are now ready to produce the well. Here, it is important to remember that the steps we take, the procedures we use throughout this process called recovery are vital in determining the present and future economic value of our pre-production well. If you recall from Chapter 5, recovery is the controlled process of bringing trapped hydrocarbons to the surface. Since it is impossible to commercially produce 100% of these trapped hydrocarbons with present technology, good engineering practices dictate that we utilize different recovery methods, both natural and man-made, over different time periods throughout a reservoir's production cycle. In other words, the term recovery is used to describe any and all methods using either natural or man-made energy sources that force the oil and gas to the surface in a controlled flow that can be captured. Chapter 10 begins with a discussion of the two sources of energy used in the initial and subsequent stages of recovery. The first source, most commonly used in recovery, is natural and is called natural lift. The second source is man-made and is called artificial lift. Defining natural lift and then describing when and why this natural lift might decrease and be supplemented with artificial lift, this chapter outlines and highlights three different types of artificial lift and mentions two others that are used less frequently. It concludes with labeled diagrams of three of the most popular systems with detailed explanations to show how each functions and why it is selected for its location and production requirements. So let's get started. Recovery, involved in the initial production stages of many newly producing wells, relies, for the most part, on the natural energy present inside the reservoir that was trapped there along with the hydrocarbon molecules as the reservoir was being created. In these newly trapped reservoirs, the pressure inside them is usually greater than at the surface in what is known as underbalanced conditions. When the reservoir is uncapped in underbalanced conditions, a pressure differential from that inside the reservoir to that at the surface causes the trapped energy along with the hydrocarbons to be pushed to the surface in what is known as natural lift. Let me show an example that you are all familiar with that will help illustrate what I'm talking about. Take a moment to visualize a column of a carbonated beverage as it explodes upwards and outwards. If you remember from your high school science, the pressure inside this bottle is greater than on the outside in underbalanced conditions. This pressure differential remains in equilibrium only until the cap is removed. On removing the cap, the pressure differential releases energy from inside the bottle. It carries with it the carbonated liquid that spews up and out. The same thing happens inside a reservoir, and this release is known as natural lift. In this illustration, you see a hydrostatic head of a fluid column that stretches from the surface to the reservoir. As the column deepens, PSI increases about 1/2 PSI per foot of reservoir depth. So, if this well were 5,000 feet deep, for example, the PSI at the bottom of the well would be about 2,500 PSI. If the natural energy of the formation is more than 2,500 PSI, then the well will flow naturally in natural lift. Know that the well's own natural energy must be sufficient to not only push liquid and gas to the surface, it must also be enough so that the well's own natural lift can overcome the hydrostatic borehole pressure and the friction created by the hydrocarbons moving up the tubing to the surface. In addition, there must be sufficient energy to push these hydrocarbons through the surface facilities. Like I said, initial recovery usually relies on natural lift. But like with the carbonated soda bottles, after the initial push, the energy inside the reservoir may dissipate and not be strong enough to continue natural lift. What can cause natural lift to slow down and fail? There are four main obstacles. The first is encountered within the reservoir itself. As you might guess, the thicker, more viscous the fluid, the more energy is needed to overcome the friction to push the fluid through the rock matrix to the wellbore. Over time, this friction, coupled with constriction that reduces the fluid volume, can cause the pressure at or near the wellbore to drop in what is known as drawdown. Drawdowns are accelerated when production rates rise and when the fluids become more viscous. The second obstacle comes about in fields with denser oils and deeper depths. The sheer volume of those heavier oils inside deep wells means that to push these to the surface, more energy is needed from the reservoir to lift that added weight to the surface. The third obstacle is specific to very deep wells with high flow rates. In these wells, just the movement of the fluid traveling up the long length of the tubing and rubbing up against the inside tubing wall creates significant friction. As the frictional force slows the oil's upward movement, more energy is needed to ensure the flow of these fluids. Finally, the fourth obstacle is encountered at the surface. Having already been pushed up through the tubing to the surface, the hydrocarbons must now be pushed into and through the surface facilities that separate and clean them in preparation for transport. This can require several hundred additional psi. When natural lift starts to falter or give out, it can no longer be relied on to get the trapped hydrocarbons to the surface and through the surface facilities. When this happens, the well's production begins to fall and then stops. When production stops, the well is said to have died. Rest assured, however, that when a well dies with commercial quantities of valuable resources still trapped within the reservoir, alternative methods will be used to bring the well back into production. This is where artificial lift can supplement natural lift. It is here that artificial lift can bring the well back into production. Artificial lift is not limited to just supplementing natural lift used in primary lift. It can also be used to supplement enhanced oil recovery, EOR, when the pressure in the reservoir falls to less than that at the surface. Regardless of the reasons for using artificial lift, the main determiner for its popularity and extensive use throughout the industry is its relatively low cost. Artificial lift relies on three main systems. The first three will be examined in some detail. The other two less utilized systems will only be briefly described. The main systems are 1. Sucker rod pumping, 2. Gas lift, 3. Electric submersible pumping, ESP. The other two less used systems are 4. Power oil, 5. Progressing cavity pumps. Let's begin with the sucker rod pumping system. Also known as the nodding donkey, the sucker rod pumping system is probably the most recognizable piece of oil field equipment. Used mostly in onshore fields because of their size and weight, nodding donkeys can easily be seen from many of the major roads that crisscross the countryside wherever hydrocarbons are being produced. The sucker rod pumping system uses a surface power source to drive a downhole pump assembly that generates artificial lift. Here's an example of a working sucker rod pump. Follow along as I name the parts and show where each is located. Prime mover, V-belt, gearbox, walking beam, Samson post, horse head, sucker rod, counterweights. The prime mover, located here, provides the power that operates the pumping system. Its power source is usually an electric motor, but field gas-fired engines can also be used when there is no ready source of electricity. The power from the prime mover is transmitted by the flexible V-belt located here. The V-belt is attached to the pumping unit in the gearbox. Note here that at this point the motion is rotational. For a sucker rod pumping system to work, this rotational motion from the prime mover must be transformed into a vertically reciprocated motion. This transformation is performed by the gears in the gearbox that is located here. These gears are attached to the back end of the walking beam located here. The walking beam pivots on the Samson post. As you can see, instead of going around and around in a rotational motion like the prime mover, the walking beam with the horse head attached goes up and down in a vertically reciprocated motion. The sucker rods are attached to the horse head that now goes up and down as it travels in and out of the hole. The counterweights located here distribute the power evenly over the up and down strokes. On the downstroke, the weight of the dropping rods lifts the weight into position, and then on the upstroke, the weight drops, lifting the rods and fluid column. So far, we have been looking at what is visible above the surface. From this perspective, basically all we can see is a device that converts rotational power into a vertically reciprocated motion. This means that the sucker rods attached to the horse head move up and down, but what is going on down below? How does the sucker rod pumping system provide artificial lift? To answer these questions, we need to follow the sucker rods down into the hole into the subsurface.